and presenting. All right, awesome. Thank you everyone so much for rejoining the Julia Health Mini Symposium. Today we are joined by Dr. Carlos Castillo Passi talking about the state of KomaMRI. Carlos, I will turn it over to you to talk about what's new with KomaMRI.
Thank you very much for the introduction. Just in case you want to see the presentation on your phone or computer, I will put the link here for a few seconds. If not, you will see it now. Okay, so why simulate MRI? I assume people here are not MRI experts, so it could be not completely apparent why would this be useful at all. So MRI has a few challenges. The MRI physics are complex and solutions often are not intuitive, so simulations are very useful for teaching MRI physics. Also, MRI scans are costly in time and money, so that makes the feedback loop of full sequence design very slow. And simulation can improve on it by simulating first and then go to the scanner. And also, sharing MRI data is complicated. There's ethics problems, patient privacy issues, and no large data set is available. For example, the fast MRI, that is the biggest one, has around 9,000 images, but ImageNet has like 14 million. So it's not really comparable, the amount of data we have for medical imaging to something that could be useful for deep learning or stuff like that. And other fields are doing, or similar fields are doing simulations, but because the cost of trial and error is very high, so they just play in this digital playground and they can answer some questions they are interested in. In our case is how we can get the faster and more useful image. So just to show you less abstractly what this means, for example, low field MRI has become popular now because it's less expensive, so it's more affordable, and it would be like more useful for more people. But the problem is that if you try to do cardiac scans in these low field scanners without doing optimization, the quality is not very good. But you can use simulations to improve the sequence parameters and get a beautiful image like this. Moreover, you can show that at the top row you have this low field image, and at the bottom row you have this conventional field image. And they have very similar image quality, and these are patients. You can also get information about quantitative information that you can extract by simulating signal dictionaries. For example, here I'm showing T1 and T2 maps that you can obtain dynamically for hearts. And what are we exactly simulating? We're simulating the Bloch equations, which is this differential equation that you can see here. And basically, what we are interested in measuring is this M, that is the magnetization, that is our measurement. And we can change B, that is our magnetic field or pull sequence. These other parameters, M0, T1, and T2, are tissue properties that depend on basically the person, not the scanner. So this is not special, it's just a differential equation. So it has a right-hand side, and we know how to solve those. But for MRI, we need to solve millions or hundreds of them. So for example, for 2D, if we have an image that is 100 by 100, suddenly we have 10,000 spins or 10,000 of these differential equations. But if you have 3D high-resolution images, we can have 100 million spins. So the computational costs start going up quite rapidly. How are we simulating this? We are using the operator splitting method to be more efficient about it and simulate faster. That basically what it does is that it separates the differential equation in two additive terms, solves each one separately, and then combines the solutions. And this has very nice convergent properties and is good enough for most cases, actually. KomaMRI implement this in a user-friendly way, and all of the things I have talked to, for example, the sequence is defined by a sequence file. The tissue parameters are defined by a phantom file. And this gets simulated by KomaMRI, and you get an output that is the raw data. For example, if you take a photo and you get the raw data, that's something we obtained before processing it and getting the final image. So we use Julia because it has very similar syntax to MATLAB, which is very commonly used for the MRI community. It has multi-threading, GPU support, and GUI support. So we implemented this in a easy-to-use user interface that you can select, for example, your sequence of interest, press simulate, and then you get your results or reconstructed image. And you can export all of this to a .mat because I know that people want to use MATLAB still, so we have made it easier by exporting it this way. One of the cool things about this problem is that all of the differential equations that I just mentioned are totally independent. So you can do each one in each thread of a GPU. And the other thing that is kind of important is that KomaMRI implemented poolseq, that is an open source definition for this sequence or how you take the image. So you have a text file that is something like this that describes each block of the sequence, and it gets parsed to something like this that describes how the magnetic fields are changing in time. And this is what's being simulated. And moreover, all of these plots are interactive, so you can zoom in and if you want more detail about one area of the sequence. So in our first paper, we basically showed that the accuracy was comparable to like sundials. That is a conventional differential equation solver that is used by Jembrys, an MRI simulator. And the accuracy is very good, and the simulation speed is like 100 or 200 times faster. Here we have more comparisons with other simulators, but basically the main point is that just by using Julia GPU array programming, we were able to be faster than existing simulators. So what's new? One of the first things we quickly realized is that it's not scalable to have a package that has everything. So we separated stuff. First, KomaMRI is the one that has only the UI definition. KomaMRI base defines the structs. There are these arrows that are passed as files with KomaMRI files. And KomaMRI core is the one that is actually doing the simulation. We added this also in KomaMRI plots to be able to visualize these data structures. One of the cool things that we managed to separate the CIs for all of this and also the code coverages. So by using tags in code coverage, you can separate them and you can have statistics in a monorepo for all of these packages. Another thing that one Google Summer of Code student did is that he implemented kernel abstractions because we were using array-based programming, so we wanted to try kernel-based programming. And just by using package extensions, what you can do is that you can simulate in the CPU just by using this code. But when you import CUDA, suddenly the KomaMRI core CUDA extension is loaded and everything is running the GPU, the same NVIDIA GPU, and the same with AMD, Apple Silicon, and Intel. And he achieved huge performance wins because he also optimized these GPU kernels. These CIs are also separate, so we can separate between JuliaCon and the LTS and all of these backends by using build guide. Julia kindly offered, and we can use Julia's computers to run this because I don't have an Apple and Intel and stuff like that. So this runs automatically in each commit or pull request. And we also do benchmarks, so we can check if there's some performance regression. As I said, we optimize the simulations by using kernel programming and basically completely optimize the speed and memory allocations of the simulator. And you can see there that by using GPU array programming, that was our first implementation, you don't necessarily get faster simulation speeds compared to CPU, like optimized CPU code, multi-threaded CPU code. But just by programming with this GPU kernel programming with kernel abstractions, you can get around 50 or 100 times faster, depending if you compare it to array-based or CPU-based simulations. Another thing that is good to note is that array-based programming, when you start getting the number of spins very high up, goes out of memory. So you are not even able to do, for example, simulations with 10 to the 8 spins. But you can do it because of the optimizations with kernel-based programming. We also included distributed computing, so we can run the simulations of a brain, for example, separated in different parts. Each one we can send to different GPUs by using distributed.jl. You get a signal that is for each one of these parts of the phantom, And the cool thing is that you can just add them together, and that's exactly the solution of doing it all at once. So this is how it looks in Julia. You basically define everywhere something similar to what I just showed you, but in the end, you just add all of the signals together for each device. And you can also send this to like a cluster by using Slurm. Pablo Villacorta from the University of Valladolid also implemented motion models, so you can simulate more scenarios regarding cardiac MRI. For example, here, he's simulating an aorta that has some flow, and you can see the corresponding signal and image. So these motions are composable. We kind of got inspired by some Julia packages about animations, so you can combine them together. So you can have translational motion that has a time range from 0 to 1, and you have another translational motion that starts from 1 to 2, and then you can combine them together. And you can see here this interactive plot of the brain basically moving right and up. So the first second goes right, and then the second one goes up. So you can combine them together. And we also have the rotations and more stuff like that, but this is just the simplest. Moreover, you can define arbitrary paths of all of these particles or spins. And this is useful for simulating more complicated phenomena like diffusion. And here, for example, you can see that the spins start all at the same position, but you can see how they start diffusing when I advance through time. So you can do quite complicated stuff. And going back to the aorta, you can simulate flow motion. So for example, here we have a coarctation that is basically a reduction of the diameter of the aorta that generates some like jet-like velocity distributions. And we simulated this with 5 million spins and using an NVIDIA GPU. And we compared ourselves to the state of the art, that is CMR sim. And we can see that we're around like 4 times faster just because we are using kernels and Julia, which made it so much easier to program all of this. This comparison is not strictly correct because we need to do some post-processing before doing this simulation to generate the particle trajectories. But after that, as that's only done once, we can just run this in 9 minutes. We can also do simulations with, for example, 7 million spins or more, and distribute this in multiple GPUs. And you can see here how the execution time scales with the number of GPUs. So we can also do distributed simulations of these like complex flows and motions. And you can do more stuff. Here I just showed a few examples, but there's more cardiac relevant things that you can do. And I just put a few examples here. So what's next? I didn't mention it, but when you generally do an MRI scan, what they put on top of you is a coil. And as you can see, it has like multiple elements. So the idea of that is to accelerate the speed of the acquisition. So each element will basically hear the signal coming from different parts of the body. So you have to reconstruct like smaller images for each one, and then you can combine them together. And we basically have this implemented in a pull request already. So you can see here like how the different coils measure signal from different parts of the brain, and then you can combine them together to get the brain, get the final image. We have also delved in enzyme automatic differentiation. So we haven't been able to differentiate Koma yet because some problems with Julia 1.11 and enzyme. But we were able to differentiate some CPU version of the code, like toy project. And we can get an RF envelope that we can simulate. And then at the bottom, you can see the actual acquisition that we did that matches the simulation. Obviously, there's a long way to go, so the RF looks a little bit weird. So if you see at the left, that's what it should look like, or approximately. So we still need to like toy with this to make it better. So conclusions. KomaMRI has been growing a lot in the last 2 years. My previous talk at 2023, KomaMRI had around 40 stars, but now it has 155, which is great. And here I put a map of a few places where I know they have used it. And obviously there has been a lot of collaborators, and this wouldn't be possible without them. also a slight propaganda. I want to show you, if you liked KomaMRI, you can give it a star. And also, please join the JuliaHealth Slack channel, because if you are interested in health and Julia, you should definitely be there. A few acknowledgements to my professors at Chile, Pablo Irarrázaval, René Bodnar, Claudia Prieto, and also a few people from Julia, like Jacob Selko, Dilum, Tim Bizard, and other people that have worked on this, and also my group at Stanford. And thank you very much.
Awesome. Thank you so much for the wonderful talk, Carlos. At this point, the floor is open to any questions for Carlos. So if anyone has any questions, feel free to ask. No? Yeah.
Okay, thank you. My name is Isaiah. Sorry. So I want to ask about the KomaMRI, the simulation part.
Yeah.
Does it simulation the functionality of the MRI, or it only simulates the imaging part?
It simulates what the magnetization would do to the magnetic field. So basically, it simulates from doing the sequence to acquiring the actual data. That's what it's trying to get, the raw data that you acquire when you do an MRI acquisition.
Oh, so if I get it right, it also simulates the magnetic field as well.
Yeah, it simulates how the magnetic field changes, and you can vary that with the sequence object and basically modify it as you like and see the results.
All right, thank you.
Hi, I'm from the Martino Center.
Oh.
So we do a lot of fMRI and MRS. I just wanted to make you aware, we have a technology known as Brain Dancer, which provides a ground truth brain activity to which you can compare the measured signal. So it provides a way to separate out thermal from multiplicative noise, which becomes important if you're modeling the MR signal, because there's scanner-specific noise that changes every time you do a scan. So I just wanted to make you aware of this technology in case it was useful to you. So Jonathan Palomani, who just moved to Stanford, he was one of the developers with us.
Oh, really?
And Larry Walt, actually.
Okay, I will definitely take a look into this. For right now, what we're doing is just simulating without considering any noise. Obviously, noise, how to simulate noise is complicated, especially if you have multiple coils. So I would be interested in looking into this. Thank you. How's it called again? Brain Dancer?
Yeah, it's called Brain Dancer because the problem is that the scanner is changing every time. And so if you use a static phantom, you can optimize over stability, but you would never want to do that for fMRI because then you'd be eliminating your signal as well. And so what Brain Dancer does is it actually produces a ground truth signal. So you can compare the measured and actual signal, learn the noise characteristics for each scan, and then subtract them out. So from a modeling standpoint, it's very helpful because it means that your data is going to be just much cleaner once you take out the scanner-specific changes that occur from scan to scan.
Yeah, that's definitely a interesting thing to explore. Like we have recently, we acquired recently a new scanner, so we want to characterize it and basically be able to simulate more realistically. And one part is, I'm not sure if this is only for noise because of the mechanical vibrations, but we want to characterize the gradients, fluctuations. So we have a way to measure it, and I'll be interested in looking into this.
Okay, we do have time for additional questions. Any more? Oh.
Yeah, so I did have one just out of curiosity.
Yeah.
You mentioned that you did monorepo CI.
Yeah.
And you also mentioned that you split the tests. So you split I'm assuming you split the tests per subpackage.
Yes.
So do you get code curve numbers from the individual subpackages? Because, for example, if you run tests on KomaMRI, that would also exercise functions in all the subpackages. So do those get added together?
Yeah, what we're doing is that the code coverage has one thing that is called flags. So what you can do is that you run the test for example, KomaMRI base and pass the code coverage to the flag base. And then you can generate a badge for each of these flags. So that's how you can get sub-package specific code coverage.
I see. So I guess what I was asking was, does the code that is covered in the tests of KomaMRI.jl make its way to the code coverage statistic in KomaMRI-base.jl?
Yes.
Oh, it does. Oh, okay.
Yes.
Oh, okay. I see. Okay, very cool. Very cool.
Yeah. So basically, like any relevant package that could touch one of these, you just add a flag, and that gets included to the code coverage flag.
Okay, very cool.
Yeah. Yeah, not a lot of people are using it, but it's kind of useful actually.
I have a bunch of other repos, so.
Okay.
Especially for GPU stuff, you can also like, we're talking about flags, and you can run the code coverage of the GPU part in build kite and send it to the flag of MRI core and gets added to the overall code coverage of that package.
I think I'll actually jump in with a question real quick, Carlos.
Yep.
So just kind of like looking future forward with kind of the results that you're talking about with comparison to state of the art, how you're like really kind of outpacing a lot of this, like some of the state of the art currently right now. I'm just curious, in terms of like future work, do you see, like, since this is so tethered into the Julia ecosystem, I'm just kind of curious, do you see like any potential roadblocks or barriers that are, prohibiting you from pursuing certain aspects that you'd be interested in exploring? Or is it more a matter of, manpower, time, implementing the work? I'm just kind of curious if you're limited by implementation or where there might be a bottleneck.
Yeah, right now we really want to do like automatic differentiation stuff, but it's just not very well documented, and so it's kind of like hacky. You need to like ask in the Julia Slack. So that is slowing down the progress a little bit, but maybe I can manage to talk to a few people here and make it work.
Yeah. Okay, any more questions for Carlos? Okay, I think that is it for questions. So Carlos, thank you so much for your time.